Micro-gestures are those split-second, involuntary body movements. Scratching your nose, tapping your foot, a quick shoulder shrug. Unlike deliberate gestures, they're hard to suppress, which makes them incredibly valuable for inferring hidden emotional states or psychological stress. But detecting them in untrimmed video, that's a nightmare for computer vision. They're tiny, brief, and easily drowned out by normal body jitter. In this video, we're breaking down DyFADet+, a new dual-stream framework that tackles micro-gesture online recognition by intelligently fusing RGB appearance with skeleton kinematics. It took second place in the 2026 MiGA challenge, pushing the F1 score to 40.88, and the secret sauce isn't just throwing two models together. It's a highly controlled, mathematically grounded fusion module that learns exactly when to trust motion data and when to ignore it. Let's start with why this task is so fundamentally difficult. Micro-gesture online recognition is essentially temporal action detection, but operating on signals with extremely low amplitude and fuzzy boundaries. You're not hunting for someone waving hello or running across a room. You're looking for subtle, spontaneous movements that might only last a few frames. If you rely purely on RGB, you get rich texture and spatial context, but you lose fine-grained motion cues. The background and natural body sway drown out the signal. If you rely purely on skeleton data, you get clean kinematics, but pose estimators are notoriously unstable when displacements are tiny. A single joint might jitter by a few pixels due to estimation error, and suddenly your skeleton stream is full of false positives. Early approaches tried graph convolutions or dual-stream transformers, but they often treated modalities as separate silos or naively concatenated them. Concatenation is a trap here. It just stacks vectors, forcing the network to waste capacity learning how to ignore the noise, and often amplifies pose estimation errors directly into the RGB feature space. So how does DyFADet+ solve this? It builds on DyFADet, which is a state-of-the-art point-based temporal action detector. The core architecture projects both RGB and skeleton inputs into a shared, multi-scale temporal feature pyramid, then fuses them level by level using a gated residual mechanism. On the RGB side, they use VideoMAE v2G as the backbone, followed by dynamic encoder blocks that progressively downsample the temporal sequence. This creates a feature pyramid where each level captures different temporal resolutions, from fine-grained frame-level details to broader motion trends. The skeleton branch runs in parallel. Raw joint coordinates are embedded via 1D convolutions, then pass through a stack of convolutional blocks that mirror the RGB downsampling schedule. Before fusion, they align the temporal lengths using nearest neighbor interpolation, ensuring every skeleton feature maps directly to its RGB counterpart at each pyramid level. Now the real innovation, the Gated Residual Fusion module. Instead of concatenating features, which just stacks vectors and forces the network to learn how to ignore the noise, DyFADet+ injects skeleton motion as a scaled, gated residual. At each pyramid level, the skeleton features are first projected into the RGB channel space, using a lightweight two-layer temporal convolution with GELU activations. Then, a gating mechanism decides how much of that motion signal to actually add. The gate takes both the RGB and skeleton features at that level, passes them through a 1x1 temporal convolution, and squashes the output with a sigmoid. This produces a per-time step, per-channel weight between 0 and 1. The fused feature is simply the original RGB feature, plus alpha times the gate output multiplied element-wise with the adapted skeleton features. Alpha is fixed at 0.5, and critically, the gate's convolution bias is initialized to -2. That's a deliberate training trick. It forces the gate to start near 0, meaning the network learns purely from RGB first. It prevents early training instability from noisy skeleton predictions, and gradually learns to open the gate only when the kinematic signal is genuinely reliable. Once the features are fused across all pyramid levels, they're fed into a dynamic TAD head, specifically DyHead. This head dynamically adjusts its convolutional weights based on the input features, allowing it to selectively fuse cross-level information without heavy computational overhead. It runs two parallel branches, a classification branch that outputs probabilities for 17 micro-gesture categories using a 1D convolution and sigmoid, and a regression branch that estimates the distance from each temporal point to the true start and end boundaries. Because micro-gestures vary wildly in duration, they generate dense temporal points using predefined strides of 1, 2, 4, 8, 16, and 32. Each stride gets a scale-aware regression range, from 0 to 4 frames up to 64 frames and beyond. The whole system is trained end-to-end with focal loss for handling class imbalance and long-tail gesture distributions, and Distance-IoU loss for precise boundary regression. The results speak for themselves. On the SMG benchmark, which contains over 3,000 annotated micro-gestures across 40 subjects, the RGB-only baseline hits an F1 score of 38.76. Naively concatenating RGB and skeleton only bumps that to 38.96. But DyFADet+ pushes it to 40.88. That's a solid 2-point gain over the baseline, and it secured second place in the 2026 MiGA challenge, outperforming last year's winner by nearly 3 points. The ablation study confirms that skeleton-only recognition struggles at 22.31 F1, proving that appearance is still the dominant signal. But the gated fusion doesn't just add signal, it filters noise. By adaptively injecting kinematics only where they're trustworthy, The model maintains stable RGB representations while gaining precise motion cues exactly when it needs them. Micro-gesture recognition sits at the intersection of effective computing, human-computer interaction, and fine-grained video understanding. DyFADet Plus shows that multimodal fusion doesn't have to be a black box concatenation. With careful architectural design, mathematical gating, and stable initialization, you can make two noisy modalities work in concert. The framework is a strong step toward real-time, robust emotion inference from spontaneous behavior. If you're working on temporal action detection, multimodal fusion, or fine-grained video understanding, this paper is worth a deep read. The challenge details and dataset links are in the description, and I'll leave a breakdown of the DyFADet baseline architecture in the next video. Thanks for watching, and keep pushing the boundaries of what AI can see.